Multicast has always been a tricky beast, so much so that even attempts to standardize on dynamic routing protocols to help propagate routing information have not had popular adoption. mOSPF, DVMRP, and a few others have not really had widespread appeal, especially in the enterprise market. As a consequence, tools that help manage multicast in large networks have been lacking. If you're one of the lucky network professionals who has had to manage large multicast video and audio networks, this is painfully obvious. What if there was a way to visually track the dynamic nature of a multicast overlay network? How much quicker do you think you could isolate issues with poor video quality or choppy audio reception? In this video, I'll show how to use Packet Design's multicast monitoring feature of Route Explorer. For this scenario, let's assume we are preparing for an important simulcast of a live corporate event, which we'll test by sending a stream from a broadcast location in New York. We have users in the Seattle office or region around there that keep getting periods of dropped audio and sometimes video, but it resolves itself in about 15 minutes. I'll log into the Route Explorer appliance using the VNC interface. I'll load the live monitored network and make a quick visual scan to make sure the network looks healthy before investigating the multicast test streaming issue. I'll then set the date and time to September 25th at 9 a.m., which was when the tests were run. To start the analysis, I'll now bring up the multicast routing status report. This is a tabular report showing elements of the multicast topology being monitored on this network. At the top level, we have the list of groups detected on the network. I'll be filtering out these so only the video and audio multicast groups will be shown. I've already created a filter called the video multicast groups to do so. As you can see, there's only a couple multicast video streams at the moment. The routers table is mostly spreadsheet style information, which can be helpful if you need to identify what function the routers perform in the multicast network. I can see here that the rendezvous point for this network is the router ord-p-121. You can also quickly focus on specific multicast events for the individual routers as well. This can help see what recent fluctuations there have been and how the flows are distributed in and out of specific router interfaces, for instance. The Igmp receivers table shows which routers have clients that want to view the multicast streams. Again, filtering for just the video multicast streams, I see the New York test stream is being viewed by clients in Chicago, Seattle, and Dallas based on which PE routers are the leaf nodes in this multicast topology. Going back to the groups list and filtering to just the video multicast groups again, I see that the 224.255.14.6 group has a source tree and a rendezvous point tree or shared tree. If I click on the source tree, I can see on the main map what the multicast tree is for this source group stream. I can also visualize this using the minimap that is part of the report UI. I see that the New York to Seattle multicast stream is using the source tree to reach the Seattle P112 router, but it stops there, which is odd since that's not the last router before reaching the client viewer we saw in the Igmp receivers table earlier. I can use the network map view in the minimap to better orient myself instead of the standard tree view used by default. If I click on the shared tree view to see which viewers are receiving the rendezvous point streams, I see that both the Dallas and Seattle clients are receiving the multicast over the shared tree. The multicast reaching Seattle P112 is probably a clue that normally the multicast traffic flows through that router to reach the client viewers instead of the shared tree path, and something is causing a shift from the source tree to the shared tree. I also see what looks like some disconnected tree branches, the gray links, so something has definitely been causing flows to shift. I can use the minimap to see how some of the disconnected leaf nodes would have normally connected into the tree by using the pull-down menu on the disconnected node and choosing to view the RPF, IGP, or tree path to connect the disconnected leaf back into the shared multicast stream. In addition to the disconnected trees, there are other tracked anomalies discovered. If a router was using the wrong rendezvous point to forward multicast traffic, then those flows would be getting rejected by the router being used as the incorrect rendezvous point. That possible misconfiguration would be caught by the RP mismatch anomaly list. That's not something that would lead to poor quality of video though. It would lead to no video at all, so that's not the case in our scenario, even though this report shows some mismatches. Another anomaly is the no PIM neighbor interface report. This shows any router interfaces that do not have PIM enabled. This would also be a catastrophic failure since multicast would not be forwarded out any interface that didn't have PIM enabled. I can double check this though. First I'll filter out any of the tunnel interfaces because I know PIM isn't running across any GRE tunnels in this configuration. I'll collapse the list so I can zero in on specific routers. I notice this list shows me a Seattle router 111 that doesn't have PIM enabled on one of its gig interfaces. After looking at it though, I can see that this is the second link of a parallel connection, so this was a conscious design decision. I also see that the Rendezvous Point router 121 has an interface that isn't running PIM. Looking at that, I notice it's an interface going into the Chicago PE router cluster. This might need further review. If any reverse paths use this exit point from the Chicago POP, then it might cause issues with the sources or clients in the Chicago POP. Right now, though, this wouldn't affect the multicast between the New York and Seattle offices. The last two anomalies don't appear to be causing any trouble. The stuck in register state only happens when the rendezvous point can't reach the source and can therefore not forward the multicast traffic. While the no PIM neighbors anomaly would be significant, all current PIM neighbors are connected. I can use the multicast path highlighting tool to show the current path of the source-specific multicast traffic for the 224.255.14.6 video stream. When I enter the relevant address information for this path profile and press OK, the path is drawn through the Chicago P122 router and then on to the Seattle POP. I can now animate any path changes by clicking on the play button to see what happens to the path during the next hour or so. During the playback, I notice a couple of key links are flapping along the multicast path. One of the links is the primary connection between the Chicago and Seattle office. I also see that the connection to the Rendezvous Point router, the Chicago P121 router, for this flow is unstable, which would also adversely affect the shared path tree. This would definitely cause poor video quality. If I was managing this network, I'd consider converting the secondary Rendezvous Point router in the Dallas POP to be the primary until the instabilities of the Chicago routers were resolved. There is also another way we could be monitoring the quality of the multicast network rather than relying on user feedback. Route Explorer will generate alerts for various multicast PIM anomalies, so a more efficient way of detecting this would have been to have an alert sent when the various PIM neighbors went down. We can also detect and alert the operators should a multicast source stop sending as well. Does this make sense? Can you see how this would be more efficient than using CLI commands to debug complex multicast issues?